Okay, so what you guys have been doing up to this point with equations, solving equation, is you've been solving and graphing now linear equations. Okay? So a linear equation is an algebraic equation in which the degree the highest degree of variables is 1. So what's this degree thing? It has nothing to do with angles. Okay? The degree of a variable refers to its exponent. So for example, if you've got this is third degree because its exponent is 3. If you've got this is second degree. However, all the equations we've been working with solving have degree 1. So this, well, what's the exponent here? I just don't write it. 1. So that means it's first degree. So you guys have been solving first or working with first degree linear relations. Okay. Next year, we're actually going to look at how to solve second degree. And then beyond that, we're going to look at how to solve third degree and possibly even higher. Okay. So we name linear equations by the number of variables of degree 1 in them. So here, how many variables? So we would just say linear equation in 2 variables. Highest exponent is all 1, we don't have to write it. Okay. What would this one be? A linear equation because the highest degree for all the variables is 1, but how many? Many variables? 3. When we have a pair of linear equations in 2 variables, so we have 2 of these, okay, we call this a system of linear equations. You don't have to know these definitions, but you do have to know what I'm talking about when I use the word system of linear equations. You can say in 2 variables, but system of linear equations is good. So basically, it's got 2 equations, and each of the equations has an x or a y. So an example of a system would be like 2x plus y equals -1, and 7x minus 5y equals 10. There's an example. What's the solution to a system of linear equations? Okay, it's the values of x and y, that, when substituted into each equation, left side of the equation equals the right side. So the left side equals the right side. So for example, I'll give you another one that's a little bit easier. X plus y equals 5, and x minus y equals 1. Here's a system. Both of them are linear equations because i's exponent is 1, which we don't write. Can you figure out what x and y are? Just look at this. Can you figure out by just sort of guessing and checking? What do you think x and y are? 2 and 3. X is 3 and y is 2. Why? Because 3 plus 2 is 5 and 3 minus 2 is 1. So when you plug it into both equations, the left side of each equation equals the right side. So the solution would be x equals 3, y equals 2. But that's not a very good method for solving these, guessing and checking, because what would the solution be to that system? Well, that's kind of hard to do in your head. Like, I wouldn't be surprised if these would be fractions, one or both of them. So obviously we need a method. And there's actually 3 ways you can solve these things that we'll talk about later. But before we do that, we're going to talk about how to set up systems, because we're going to be doing a fair amount of problem solving with this. So here, let's look at how to set up a system with 2 equations in problem situations. So we've got this situation. School district has buses that carry 12 passengers, buses that carry 24 passengers. The total passenger capacity is 780, and there are 20 more small buses than large buses. So we've got 2 unknowns here, buses. We've got large buses, which we're going to call L. We'll use that letter. We've got small buses, which we're going to call S. Now somehow, I have to make up a system using all the information in this equation. So I have to make up 2 equations. So let's look at the first one. The total passenger capacity is 780. How would you calculate how many students are on the large buses? We don't know how many there are, but how many are on each large, or sorry, how many are on each large bus that can carry? Large bus can carry how many? 24, okay? So wouldn't the number of students on the large buses be 24 times however many there are? What would be the expression for the number of students in all the small buses? 12Fs. If I add those together, don't I get the total number of students or total capacity? Which is 780. Notice how I constructed an equation from this and this. I got to construct one more equation, and hopefully you see somehow I've got to use this. There are 20 more small buses than large buses. Remember, we called the small S and the large L, right? So how can we turn that into an equation? There's 20 more small buses than large buses. So we got more small, right? So if I were to take the number of small and subtract the number of large, what number will I always get? 20, right? Isn't the difference between them 20? So doesn't that mean that the number of small buses minus the number of large must always be 20? Because there's 20 more of these. There is your system. Okay, so you see how we can set up a system given a word problem. There's always going to be two unknowns. And there's always going to be two equations. And you'll always be able to create the two equations from all the information in the problem. Now, the second part of this is, okay, let's say, remember we haven't learned how to solve these yet, but let's say somebody solved it and they figured out, okay, there's 35 small buses and 15 large. How could we determine if this is actually correct? In order to do that, we got to plug it into both of these. So we got to check these equations. We're told that there's how many? 35 small, 20 or 15 large. So if I do 24 times 15 plus 12 times 35, that has to work out to 780. If it doesn't, this is wrong. So does 24 times 15 plus 12 times 35 equal 780? I don't know if this is true yet, so this is what I'm going to put over the equal sign, a question mark. So I'm basically saying, does this equal this? Well, let's do it. Somebody got a calculator? 24 times 15 plus 12 times 35. 780? Somebody got it? Yep. One more person. Yep, 2 people. So 780 equals 780. That equation works. So it works there. But does it work in the other one? Does the number of small buses, which is 35, subtract the number of large buses, 15, equal 20? Well, that one's pretty obvious. 35 minus 15 is 20, and it does equal 20. So what have we done? We have verified the solution. So yes, it is the solution. Whoever calculated it did not make a mistake. That's really what we're going to focus on here for today to start, before we start figuring out exactly how to solve these things. So let's look at a few more examples. Okay, next one. Here's the situation. The perimeter of a Nunavut flag is 16 feet. Its length is 2 feet longer than its width. What are the two unknowns here? Length and width. So that's the first thing we're going to do, is we're going to say length is L, width is W. So my equations are going to have an L and W in each one. And you can kind of see it in the question. This is going to tell me my first equation. And this is going to tell me my second one. It's always going to give you enough information. How do you find the perimeter of a rectangle, which is a flag? How do you find the perimeter of a rectangle? How do you find the perimeter of a rectangle? That's area. Add up all the sides. So would you agree that there's 2 lengths and 2 W's? So maybe to make it a little bit cleaner, 2 lengths plus 2 widths must work out to 16 in this case. There's one equation. Now the second equation, I'm going to use this sentence. I would suggest you always write it as a subtraction. Okay? Which one is higher, length or width? So that's going to tell me I'm going to do length minus width. It's always, whatever one is higher goes first in the subtraction. And then what will it equal? It will equal how much more? How much more is it? 2. Done. That's it. You set up your system. In part B, we're asked to verify. We're told that Denise figured out length was 5, width was 3. So we want to verify this is correct. So does 2 times 5 plus 2 times 3 equal 16? Yes, it does. Does 5 minus 3 equal 2? Yeah. Verify. All right. Okay. Next one. A school raised $195 by collecting 3,000 items from recycling. And what did they recycle? Pop cans and plastic bottles. And they got 5 cents for each pop can, 20 cents for each plastic bottle. What are the 2 unknowns? What don't I know? How many there are? Cans and plastic bottles. So we'll just put cans and bottles. And we'll call them C and B. You can call them whatever you want. You can call them whatever letter you want. Okay, so somehow I've got to take all the information in the problem and create two equations. What's the total number of cans and bottles? 3,000. So how would you put that into an equation? The total number of cans and bottles is 3,000. Sorry? C plus B equals 3,000. Exactly. Oh, interesting. The next one is a little bit trickier. How much do they get for each can? 5 cents, and for each bottle, 20 cents. So if I calculate the total number they get from the cans, the total amount, and the total number they get from the bottles, what's that going to add up to? 195. So I know it's going to equal 195. Now, this is where it gets a little tricky, because you may think to yourself, okay, so they get 5 cents for each C, so 5C plus 20B, that must add up to $195. What's wrong with this? What's wrong with this? They're not the same units. This is cents. This is dollars. Right? So this equation is not quite right. How would I change this? Like this is in cents, this is in cents. How would I change this from cents to dollars? $195 is how many cents? What would you multiply by? How many cents in a dollar, even though we don't use the cent anymore? 100. So multiply this by 100. That's better. 19,500. Now everything's in cents. Or you could have changed these to dollar form, but then they become decimals. Still right, but I'd rather work with whole numbers than decimals. And now we just have to verify. So this is what was reported, 2,700 pop cans they collected, 300 bottles. We want to see if that actually is true. So that's 2,700 plus 300 equal 3,000? Absolutely. That's 5 times 2,700 plus 20 times 300 equal 19,500. Well, that's I'm not so sure about. So that I'm going to have to use a calculator to make sure that's right. So I'm going to have to do 5 times 2,700, which should be 13,500. This is 6,000, so 13,500 plus 6,000. And if you use a calculator, it will work out to 19,500. So we're verified. We're verified. Life is good. Okay, last question. So a store display has packages of 8 batteries, which are called E, and 4 batteries, which are called F. We are told that the total number of batteries in a display was 320, and there was 1.5 times as many 4 batteries as 8 batteries. So Herman came along, set up the following system. And he solved this system, and he determined there were 30 packages of 8 batteries, 20 packages of 4 batteries. Okay? Well, let's verify that he's correct. So he does 8 times 30 plus 20 times 4 equal 320. This is 240, this is 80, add those together, we get 320. That's good. And that's 1.5 times the number of 4 batteries, which is 20, equal 30. Well, 1.5 times 20 does work out to 30. So that works. So it seems like everything's good. But Sherman came along and he said, no, you're wrong. Question is, who's correct? Think about Herman's solution. Like, it seems like this is okay for his equation, but it's that second one. There were 1.5 times as many 4s as 8s. Okay? 0.5 times. So there's more 4 battery packages than 8s, right? Yeah, look at Herman's solution. We got more 8s than 4s. Which is wrong. This is wrong. This can't be. So where was the mistake? Well, the mistake was actually here. It should be 1.5 E equals F. Because remember, there's more 4s. So that means we're going to have to multiply the E's by 1.5 to get to the number of 4s. Okay, so Sherman is actually correct. Because the second equation should be the other way around. It should be 1.5. Yeah, 1.5 times E equals F. This makes more sense because we have to multiply the E's to get up to the number of 4s because there's more 4s. Okay. Okay. That's it.